short introduction into BrainScaleS 2 software, and I try to give a short overview of the hardware, so the basic properties, and the use cases that we try to cover with the system, how to access the system, and how we integrate into eBrains. eBrains is an infrastructure project. And so it's a tutorial session. So if you have questions, feel free to interrupt me and also to ask us, or ask me. I can also divert to my colleagues here with active video streams. So let's just start. So BrainScaleS, most of you, or some of you might already know, it's a neuromorphic system, physical model. So this means we have analog circuits that model neuron behavior in terms of a physical model. So there's, for example, a membrane capacitance that is modeling the cell membrane. We have a simplified neuron model. In this case here, it's adaptive exponential integrating fire. We support short-term plasticity. We have, in this hardware version now, structured neurons, so you can build neuron compartments and have different topologies in your structured neurons. There are nonlinear effects on the dendrites that you can make use of. We have accelerated model dynamics, so this means that our neuron membranes have typical time constants in the order of microseconds instead of milliseconds. So let's say 10 microseconds instead of 10 milliseconds in typical biological neurons. We support online updating of neuron parameters. So there are analog parameters like, for example, the leakage potential or similar things that can be updated at experiment runtime. Can be, for example, used for homeostatic plasticity or similar stuff. We can also update network topology in general during network operations. There are also publications that make use of this feature, in particular structural plasticity. We have programmable plasticity in general. So there are two plasticity processors, or SIMD vector processors embedded on the system, on the ASICs, on each ASIC. On the left here, if you can see my mouse pointer, can you see my mouse pointer?
Yes.
Okay, good. That's basically the ASIC that we have here. There are two hemispheres, basically because this is how hardware design works. So our hardware developers build basically one hemisphere and they just mirror it onto the other side of the chip. And then we have twice the area in terms of synapses. That's this nicely looking rectangle here, and also on the other side of the chip, and there are neurons in the center in two rows, and these neurons can be interconnected for this multi-compartment stuff. The SIMD processors are also located somewhere, I don't know, probably on the top and very bottom here, and they have also access to parameters that are available on the chip. Yes, but it's not only plasticity that you can work with on these programmable processors, but you can also run arbitrary code. So if you are able to compile standalone code, you can run anything on it. In general, the chip also supports non-spiking operation. So we have basically an analog multiply accumulate unit here that can be configured. We won't show this in this tutorial here, but the hardware supports it. Yes, so in terms of systems, we have multiple system types. We have a lab setup that's on the left here, which is basically hosting the chip under this white dust cap, some carrier boards. Yeah, you have to ask the hardware specialists for the details about these boards. And at some point, there are FPGAs that basically provide an interface between the host and the chips here. We also built an embedded system. We have showcased the embedded system last year. Johannes Schemmel also gave some details about the mobile system. It's aimed for embedded operations, so it's a credit card sized system. In terms of the rectangle here, it's obviously thicker than a credit card, but it aims for embedding and mobile operation. In general, we design our systems to nowadays to be really something like accelerators. So for spiking neural network operation, for example, but also, as you heard on the slide before, artificial neural network operation. And they are in general network attached. So this means typically we have gigabit Ethernet networking going on between the host computer and the systems here, or the FPGAs in particular. But we also have different interface technologies like XTOL that provide, for example, lower latency interfaces and higher bandwidth. Our software stack provides varying abstraction levels. So there's the high level stuff like PyNN or Pine, it's pronounced Pine, sorry, which is a Python-based API that is popular in the computational neurosciences, I think. We also have something which is called hxtorch.snn, which is our extension for PyTorch, and it provides a particular layer that allows us to model spiking neural networks with it. There are also many other layers between this high-level stuff and basically the lowest levels where you have access to single bits, and they can be used for different kinds of hardware abstraction, for hardware commissioning, for hardware development, for software development, and similar. So in terms of what does an experiment consist of on our hardware, so typically we mean something like a configuration, so basically, for example, a weight matrix, but also the parameterization of our neurons. And as you remember, we have adaptive exponential integrating fire neurons. So this means you have 5 parameters that you configure in the mathematical model. In our hardware case, we have many more because there are also technical hardware parameters. And in general, I think we have in the order of 20, 25 or something like this parameters that are configuring one individual neuron. And there are 512 neurons available on the chip. There are also shared parameters, global parameters that are basically not per neuron, but change behavior on quadrants or on hemispheres of the chip, or maybe also on the chip global scale. So for example, clock speed is a chip global parameter. There are also I/O functionalities like spike trains that you can send in as stimulus and also read out, record. There are also other observables. So for example, you can enable some ADCs, on-chip ADCs that record membrane potentials or other more technical parameters. You can also
have some kind of echo, Eric. Do you have?
I have echo.
No, I think it's not you. It was somebody else who had his microphone.
Okay.
But he muted himself now.
Okay, good. Then yes, I think I clicked one time. Okay, so the chip picture is gone and it's more of a schematic. So there are also observables like these membranes that we can record, but also controllables. As I mentioned, we can update at experiment runtime. We can update some of the parameters. And controllers that basically modify or provide input to the chip can be the host computer, the FPGA, but also the embedded processor. So it's really some kind of distributed controller system. Yes. Okay. In terms of software tasks, what we have to do is basically we have something like a graph-based description of the experiment in terms of topologies. For example, you have certain amounts of neurons in different configurations. You connect these neurons into a graph, and at some point you want to configure this down to the hardware. And basically the task that you have to solve here is a placement and routing task. That's what our software internally does. You could also parameterize the neurons. For example, you could want to have, let's say, biological parameters, or at least SI unit parameters like 10 microseconds for time constants. And then the software runs and performs parameter translation internally. That's a feature that basically is not used in the tutorial later because it's not available in our software yet. But in general, that's one of the basic tasks that we work on and which will be available soon, but it's not in part of this tutorial later. So in the tutorial, you will have to work with low-level values that are directly programmed to the chip. But the topology conversion is happening automatically. Plasticity kernels, so basically this is plasticity descriptions for individual parts of the network, also need to be translated to programs for this embedded processors. And then we have the I/O things and other dynamics that could also come in from the embedded processors. In terms of experiment execution, this means that now time flows from top to bottom. We have the host computer, we have this initial configuration or static configuration, it's called static configuration here. And we have basically something like a time evolution program. So that's the real experiment part, so basically your runtime of the experiment. Both are packed into so-called playback programs because they are played back by the FPGA. We transfer those to the system, and here the system is basically everything, so FPGA plus the ASIC, and we execute it. So that means basically the host does not have control over the execution here, but it's the FPGA that orchestrates the experiment execution, and we get the responses back, and we do additional computation like translating timestamps to biological milliseconds of experiment runtime or similar. Yes, I will skip this. So just to give an overview of the layers, we have basically the high-level modeling layers like Pine and PyTorch that are aiming for neuroscience and machine learning applications, but we also have this many more layers that are used internally by our experts here in the group, but also other experts. And we will use some of these interfaces for some of the experiments later. Yes, so one teaser for the demos or for the tutorial later is that we have structured neurons. So if you think of this tree here, this simple structure where you have basically two compartments, and the second one is branching into two chains. This basically can be translated to hardware configuration. If you think of the chip layout, if you remember the chip layout, I said that there are two neuron rows in the center of the chip, and this basically is a representation of these two rows. So in the top row, we use basically 8 circuits, individual ADX neuron circuits. And in the bottom row, we use 5. And they are connected using these horizontal bars and also using resistors, configurable resistors in this. Sorry, I have to use my mouse here. Using these connections here. And on the right, we have some PSP shapes that change depending on the injection site. So if you inject in the orange compartment, it looks like this here in the top panel. If you inject at the second, this brownish compartment, the PSP shapes look a bit different. And yeah, you will be able to play around with this later. We also support programmable plasticity. So this means if you know how to write embedded C++, that's basically this string here, this red text string. So if you can write this in C++, our software stack allows you to cross-compile this for the embedded processors, and they will run it. And this is basically exposed to Pine using this kind of opaque type system where we introduce a homeostatic synapse. It's just a name, and we basically describe the behavior in some kind of C++ plasticity kernel. And all the magic that happens is basically encapsulated into these two function calls. We define basically this plasticity, it gets cross-compiled, and by providing a particular projection, that's the Pine terminology for connection between two populations, we can assign this plasticity kernel to individual synapses, and during experiment run, they basically this plasticity kernel is applied on these synapses. And on the right, there's just a small test where we see this kind of homeostatic plasticity going on, and it basically stabilizes the firing rate of a set of neurons. Modeling in PyTorch-like environments is also nowadays an interesting topic. So we want to model basically hardware in the loop kind of experiments. So this means that you, for example, want to have hardware execution for your forward pass in your machine learning setup. And for the optimization step, for the backward pass, you want to basically have arbitrary, you want to inject arbitrary functions in software, and that's possible using this API here. We are currently working on this, and in the end, we basically aim for something that is composable. So this means we don't destroy functionality that PyTorch already provides. So, for example, auto differentiation should be still available, and we want flexibility to be able to inject this autocrat capable functions for the backward pass. And the future step here is we aim for an integration into Neurons, and Neurons is another API for modeling with spiking neural networks on PyTorch. And it already supports GPU-based acceleration, more or less obviously, and it's also nicely benchmarked. Christian Pehl is one of the authors here. So it's an interesting API, and yeah, we aim for it also for BrainScaleS 2, for BrainScaleS 2 backend. Platform access. So nowadays, BrainScaleS hardware and the hardware of the group before the BrainScaleS architectures have been accessible for external users. So since a long time, I think since I joined the group, which was in 2007. So for a very long time, we have had external users. Nowadays, we leverage eBrains central services, and by central services, I mean AAA. So that's accounting, authentication, authorization, and accounting of users. So basically, you can sign up as a scientist. You can sign up for an account if you get one, and you basically you are able to use the eBrains services. And one of the eBrains services that we will also use for the tutorial afterwards is a web IDE. It's Jupyter Lab. It's not the most sophisticated web IDE that is available on the planet, but it's one of the most commonly used ones, and that's the one eBrains supports. There's also storage, quota, job reporting, and in the end, there's also user support. So high-level user support, and they dispatch you to the individual components that you are using within eBrains. And in particular, this means that BrainScaleS hardware, and this means every version of BrainScaleS is available or accessible via eBrains, but there's also, for example, Spinnaker. There's also a Spinnaker tutorial at some other point in time during the NICE conference. I forgot the date and time slot, sorry for that. But Spinnaker is also accessible via eBrains. And there are many other software packages like spiking neural network simulators and other tools that are also available via this eBrains central services. We also created an experiment service for this, for BrainScaleS 2, to allow for interactive experimenting using this central services. And that's what we use in the tutorial later. And we aim for example, 10 Hertz experiment repetition rate, but this depends on the specifics of your experiment and also I/O. In general, what we did for this, or what we worked on for this for the better part of a year, is basically to get our BrainScaleS 2 software stack integrated into eBrains. And for this to succeed, we convinced the eBrains team to adopt Spec as a package manager, because we internally use Spec as a package manager, and it's really a nice tool to explicitly track your dependencies of your software package. And because of this process, it was in the end very easy to add BrainScaleS 2. And a nice side effect of this is that we will also have this eBrains software distribution. I call it eBrains software distribution. It will be deployed to the eBrains HPC sites, and there are several of those European HPC sites, so like Jülich, CSCS, Barcelona Supercomputing Center, and others. I forgot them now. And this will enable multi-site workflows. So if you have difficult experiments that involve GPUs, CPUs, maybe not only farming, but also distributed computing, parallel computing, and you want to combine this in a tight loop with neuromorphic hardware, then this might be interesting for you. Disclaimer, obviously this, obviously that's the perfect state, what we have currently is that eBrains, the eBrains software distribution, is still somewhat, I call it stable. Like think in, if you know Linux distributions, think of Debian stable. No, it's not as bad, but it's already half a year old. We expect this to change in a couple of weeks because we are now adopting a better release scheme, and additionally there will be also testing deployment that will allow for more continuous stream of newer software versions. And there we aim for weekly deployments. So there will be much newer software in the future. But in the tutorial afterwards, you will work with software that is at least 0.5 years old. Yes, many other features that I presented here, like this multi-compartment neurons, the high-level interface, programmable plasticity, and the spiking neural network support is still under development. So this will at some point materialize in a stable release, but at this point in time, it's still somewhat under development. So to conclude, we basically work towards multiple goals. So first of all, we want to establish or provide software functionality for all BrainScaleS 2 hardware features, and that in particular means structured neurons and the multi-chip systems that we are currently developing. Programmable plasticity, the machine learning friendly interfaces, and also efficiency. I didn't show this, but we also work on efficiency. So for example, fast reconfiguration if you change only parts of your experiments, and you want a high repetition rate, that's also what we work on. The parameter translation I mentioned before. And in general, we also continue to work on system robustness. Yeah? And that not only means hardware robustness, so that your experiments run smoothly and with high probability, success probability, but this also means, so for example, software stability and service stability of this experiment service that we are providing. And in the end, we want basically neuromorphic hardware to transition towards basically a tool for all kinds of science, and which has a flatter learning curve for new users, yeah, because in the past it has been hard for all users. And that means deployment, the operation, and also the usage of the system. We will make use in the tutorial afterwards, we will make use of basically executable documentation that includes examples, and it focuses on our Pine API. So it won't focus on the HXTorch API, but only on Pine. And almost all of you should have received an email with a link to, which looks like this, so basically wiki.ebrains.eu, and at the end there is some NMC minus test minus some username folder. And this folder should give you access to our tutorials, which will start soon. My very last slide is just a teaser for an upcoming publication. The preprint is available on arXiv, which covers our software stack. And there are many names on it because it's a large software stack. And thanks for the time.